Hi, my name is Adolfo Jasso Campos, and today I will explain the experiment of the tuning forks. First of all, we need to understand what is a tuning fork. A tuning fork is this thing shown here in the image. Basically, when you make it vibrate, it produces a very specific sound. Uh, what we're trying to do for this experiment is to understand how exactly does this work. On the first part of the experiment, we will see how a tuning fork can create resonance with another tuning fork. On the second part of the experiment, we will see how two very slightly different sound waves can create a beat. A beat is this thing shown on graph C. But as for the first part of the experiment, we will actually do what is shown on the image on the left. As you can see here, we have two tuning forks, one on the right and one on the left. On the left, there is a small aluminum ball attached to the second tuning fork. We need to what we're going to do is make the one on the right vibrate, and to see if that makes resonance with the second tuning fork, which in turn should make the little aluminum ball vibrate. So here is the video of the experiment. As you can see, we hit the tuning fork with a small hammer. You can see here that the aluminum ball almost immediately started going from side to side of the second tuning fork, and as soon as we stop it, it stops moving that much as well. This is because the first tuning fork created resonance with the second tuning fork. It basically made it vibrate even though we didn't touch it, and because it vibrated, it made the aluminum ball vibrate as well. But because it is not in sync with this tuning fork, it just goes up and side to side while it seems randomly. But as soon as we stop the vibration on this tuning fork, the second one also stops, making the vibration on the aluminum ball also stop. It doesn't stop immediately because of conservation of momentum, but it slows down very quickly. So in this experiment, we proved that effectively the two tuning forks can create resonance between each other. So now for the second part of the experiment, we need to understand the basic concept of a beat. Here on graph A, we have a sound wave with a specific period. And on the second graph, on graph B, we have another sound wave with a slightly different period. If they were the exact same period, if we reproduce them one next to each other, it could create double the sound, or they could cancel each other. It depends on how much phase difference is between the two of them. But as they have very slightly different periods, therefore very slightly different frequencies. Remember, frequency is 1 over the period. This creates this type of wave. As you can see, it has what it seems like two different frequencies. One, which is the normal frequency or period that we know, which also happened on the first two graphs. And there appears to be a second period or frequency, which is this one right here, because the wave for a time it doesn't get as intense, but in another time it gets very intense comparatively. This is repeated a long time. So we can say there's a second period between these peaks in intensity. Now, how do we calculate them? Basically, if you follow the formulas, you will eventually derive that the frequency of the beat, which is the frequency or the period from the very intense parts of the wave, can be calculated as frequency 1, which will be the frequency of the sound wave, minus frequency 2. And as for the small frequency, which is this one right here, the formula is the average between the two frequencies, and we call that frequency n. So what we're going to try to do is use the two tuning forks, make a very slightly different sound wave, in order to create between both of them a bit, and then see if the bit behaves the way that these formulas theorize. So here's how we set up the experiment. Here, as you can see, we have a tuning fork and another one right here. For the second tuning fork, in order to make it a slightly different sound, we attach a small clay ball to it. This changes its mass, and therefore the energy doesn't make it vibrate as much, so we produce a different sound wave with a different frequency. We also have this sound sensor that can record time and the intensity of the sound. This is connected to this Pasco machine, which is connected to a computer, which shows with the Pasco program shows us a graph of time versus sound intensity. And we also, when the experiment is being done, are going to record a graph with instead of time, the frequency versus the intensity. How this machine is able to do that? It is because it performs a fast Fourier transform to the time graph in order to convert it into a frequency graph. Therefore, we will have the frequency of each of these tuning forks, because first of all, we're going to record only one of them, then we're going to record the second one, and then we're going to record them both by having the sound being in the middle of the two. So here is the graphs we got. On the left, we have the graph for the tuning fork 1, the one without the clay ball, and on the second one, we have the graph of the tuning fork 2, the one with the clay ball. So as you can see here, they are really similar. Around the same amount of time, about 11 milliseconds. They produce around the same sound intensity and have around the same amount of peaks and valleys, therefore a very similar frequency. But they are actually they're actually very slightly different as we intended. Here you can see their Fourier transforms. This was made using this Python program, which first of all we need to know the length of the sound intensity. Therefore, how many times how many values we got, how many we recorded, and then Fourier transform is performed on that size of recordings. For the x-axis, we also said how much time it happened between each one of them. This was done using the library of NumPy on Python. So here is the Fourier transform for frequency 1 and the Fourier transform for frequency 2. As you can see, they are also very similar, around 0.5 kilohertz. So therefore, what we did was use the values from these graphs right here, the ones of time, and we got the maximums and compared them between each other in order to get the average period. And as you remember, period is equal to 1 over the period is equal to the frequency. So this is how we got the frequency. So here is our results. Here is of tuning fork 1, and on the right is the one of tuning fork 2, the one with the clay ball. As you can see, we got the average of 5 different peaks of each other, and we got this period. As you can see, the one of tuning fork 2 is slightly higher because it takes more time to produce with the same amount of energy to produce the sound. So therefore, it has a higher period. The uncertainty was calculated for the periods using the formula of uncertainties for average, which is the standard deviation between the values divided by the square root of samples. As for the frequency, we just divided 1 over that frequency, 1 over that period, sorry, and because the period was on milliseconds, which is seconds times to the 10 to the minus 3, 1 over this makes 1 over seconds, or hertz, times 10 to the 3, which is 1000, which means this is in kilohertz. How we got this uncertainty was using this formula, which, as you can see, the calculation was done by taking the inverse of the original value. Therefore, its derivative was minus 1 over the original value squared. So therefore, the uncertainty was the absolute value of the original uncertainty divided by x squared. So that's how we got the uncertainty for the frequencies. Now that we have these values, we can actually get the theoretical frequency n and the theoretical frequency bit, which, as you remember, was using these formulas. The first one, as you remember, is an average, so we use the uncertainty for the average. And as for the bit, because it's a sum, we actually need to use this formula for the uncertainty of sums, which says that the sum, or in this case, the subtraction, is equal to the square root of the uncertainty of the first value squared plus the uncertainty of the second value squared. We now have the theoretical values for what the bits should be, their frequencies should be, but we also need to get the experimental ones. So here are the results. As you can see, this is the graph of the bit. First of all, just by looking at this graph, you can very clearly see it does represent a bit, as we saw on some images ago, what a bit should look like. And as you can see, we can also see the small frequency, which remember is frequency n, and the long frequencies, which are frequency bit. So when we make the same calculations we did for the previous ones, for the previous graphs, we get that the experimental period n, remember this is the small one, was around 2.24. The same calculations we made using the same uncertainties, the one for averages and the one for the inverse. We also took 5 values and averaged them for the peaks, and we got around 0.429 kilohertz. So when we compare this to the theoretical value of frequency n we got from the previous graphs, that was around 4.447 kilohertz, we get an error of 0.0397 kilohertz, which comes around comparatively to the theoretical value of 8.87%, which is actually really low. Now, when we get the experimental value for the period of B, we get 43.2 milliseconds, which is much higher than the period for for period of N, because it's longer. As you remember, on the graph, there are the one for the bits itself, for the peaks of intensity is much longer. So when we get the frequency, because this is much higher, therefore this one will be more longer, remember, more shorter, because remember it's an inverse relationship. We also got this uncertainty is a little different, as you can see. Here the uncertainty is much higher, because as you remember on the graph, you only got we can only get 2 real values for the peaks of the bit. Let me show you here, right here. We could theoretically use the last recording as a third bit, but we aren't sure of that. Maybe it's the next one, for example. So we only calculate using this one and this one. So it's not really an average, it's more of a subtraction. So that's why the uncertainty is much higher, because we use the uncertainty for subtraction, which we saw on the last graphs also. For frequency, it's the same formula for the uncertainty. And when we compare this to the theoretical value we got of 0.0232 kilohertz, the error is of 0.00246 kilohertz, which is much lower than the one on the frequency n, but because it's much lower also the original values, the error comes a little bit higher at around 10.63%. But in my opinion, it's still a really low error. As you can see here, the experimental values we got are very similar to the ones we calculated as theoretically. This is because although there is some interference with loss of energy due to friction or other sounds on the room, etc., they do not affect that much the graph on itself, the bit on itself. So therefore, that's why we got really close values, and therefore the formulas we got for the tuning forks are confirmed experimentally. Thank you for watching.